welcome everyone. If you're already here, welcome to the talk. Thanks everyone for coming. We're going to go officially live and start the presentation in a minute at 4. But for now, I just want to thank everyone for being here, and much thanks to the Blockchain Center, who is co-sponsoring this event. And yeah, I'm really excited to be here today to talk about introduce you guys to cryptography, blockchains, and zero-knowledge proofs for finance. So before we get started, since there's not as many people here today, we can actually make this presentation a lot more interactive. So I would be happy if anybody who's here wants to submit questions during the talk in the chat box. I'll be happy to try to answer those as we go, so that hopefully everybody can learn as much as possible. Are there any questions to start off? All right, let's get started. So, like I said, thank you guys for having me. My name is Eli Jaffe. I study cryptography at UCLA with Rafi Ostrowski, and I specialize in cryptocurrencies, zero knowledge, and multi-party computation. I'm really excited to be here today to talk about all of these exciting topics, and particularly how we can apply them to finance, and how these concepts work together to make transactions on a blockchain both confidential and auditable. So let's get into what that means. So first of all, let's talk about some basic cryptography. What is cryptography? Well, cryptography on a very basic level wishes to answer this question: how can we utilize our data but also keep it private? One simple example of a cryptographic protocol is the situation where Alice wants to send some data to another party, Bob, without revealing that data to any eavesdropping listeners on the same communication channel. So here we have Eve, who's trying to figure out the message M as Alice sends it to Bob. Now, we can solve this problem by introducing some information, a secret key that's shared between Alice and Bob. So Alice and Bob now both hold this secret key, K, and Alice modifies her original message M using this secret key and sends the new encrypted ciphertext to Bob, who uses his copy of the secret key to decrypt the ciphertext back into the original message M. Now, Eve, our eavesdropper, who does not know the secret key K, just sees the ciphertext, which looks random, and learns nothing about the original message. So encryption is one of the oldest cryptographic problems, and there were many flawed solutions actually before there were any good ones. So for example, Roman generals used to tattoo messages onto the scalps of their messengers and then let their hair regrow and then send them off to deliver the message, in hopes that whoever captured them, an enemy, would not think to shave their head and look for the message. But not only is this a very inefficient way to encode a message, but it's not even secure if your enemy knows what method you're using to encrypt. This is called security by obscurity. You're only secure if your opponent does not know what strategy you're using. So I think we can agree that this is not a good encryption scheme. But as time went on, we developed some more sophisticated methods. In World War II, there was a very famous encryption scheme called, or piece of hardware called the Enigma machine, which essentially had a very complicated internal state according to a complicated set of gears, and it would use that to map each letter to some other letter. So I type P, but maybe it comes out R. And the other person can decrypt the message by using the same internal state represented by a couple numbers. The issue was that this machine never mapped the same letter to itself. So if I type an R, it will never actually come out as an R. And while that may seem like a really small mistake to make, actually this was what allowed Alan Turing and his team to deduce the key every day from the first message sent. They used this weakness along with the fact that all messages generally started and ended the same way, to every day figure out exactly what the key was and turn the tides of the war. So, both of these methods kind of exemplify this issue of unproven security, where I have a scheme for hiding information and it seems secure based on my best guess and everybody else's efforts around me, but eventually somebody figures out how to break it. Now, obviously things must be much better today. So what does cryptography look like today? Well, first of all, every well-respected piece of cryptographic software or cryptographic protocol is what we say provably secure, meaning that it gets its security from some well-studied and widely believed mathematical assumption. Some of these include, that discrete log is hard, that factoring big co-prime numbers is hard, that these other problems are difficult, called learning with errors or the discrete Diffie-Hellman assumption. So all of these are problems in mathematics that have been attempted to be solved for a long time and nobody's had any luck. So essentially what modern cryptographic protocols say is that if you can break my protocol, if you can break my security, well, you've also in the process solved this 100-year-old math problem. Which I think we can all agree is probably very difficult. And beyond provable security, we've gone much further than simply encrypting messages. So, for example, we have pseudorandom generators and functions whose output is actually computed deterministically, but looks random to any practical observer. So any machine that tries to figure out whether a string is pseudorandom or random is going to have a negligible probability of figuring it out. We also have homomorphic encryption, which is similar to encryption as I just described, but you can take two ciphertexts and you can multiply them together, or you can add them together, and the message that's inside the encryption will actually be multiplied. And so this allows us to compute arbitrary functionalities, as breaking them down into pluses and multiplications without ever unpacking the ciphertext into their original message. We can also do what's called a multi-party computation. So this is something I study, where a large number of mutually distrustful parties each hold some private piece of data, and they want to learn some function on that combined data. But nobody is willing to share their data with any of their peers. And so with multi-party computation techniques, we can actually guarantee that everybody can learn the output of the function, and nobody will learn anything more than the output of the function, in particular, anything about anybody else's inputs. And we can digitally sign things. So if I have a piece of data, I can produce a signature on that data such that anybody else who looks at it can quickly and easily verify that it was really me who signed it. And then all of these technologies, in different ways sort of come together to create blockchains and cryptocurrencies, which are these kind of complex cryptographic systems that give particular guarantees. And we're going to talk about that now. Okay, so I'll pause here for a moment and make sure there's no questions. All right, so let's talk a little bit about blockchain now that we sort of have a handle on what cryptography is. Now, we're mostly going to be talking about blockchains today in terms of their properties and their functions. But in future talks, we might discuss more of the technical details on how you actually construct a blockchain from these various cryptographic tools that I mentioned. So to start off, what is a blockchain? Well, on a functional level, a blockchain provides a public, decentralized, append-only ledger. Okay, so it's public, which means that any data that's posted on the blockchain is available to any participant in the blockchain. It's decentralized, meaning that the data on the blockchain is not held by any one party in particular. In fact, everybody simultaneously stores the blockchain as a group. and it's append only in the sense that data is never removed from the chain once it's been approved by the protocol. It's only ever added to the end, and you can add some new information that might update what you previously said. And it's called a blockchain because we organize the data, traditionally in this sort of series of blocks, which are tied together, usually by some kind of digital signature. Okay, so we know sort of what a blockchain is on a very high level, but why would we care about such a thing? Why would such a thing be useful? Well, right now we already have ledgers. It's just that they're centralized. So instead of having a ledger that's controlled by a large group of people, we have ledgers that are controlled by single parties. So for example, my bank has a ledger of me and all of the other customers of the bank, and they have all of our personal information in that ledger and all of our financial history, and they can do whatever they want with it. So as you can see, the primary problem with centralization is that they're not only vulnerable to abuse internally, but attack from the outside. It's very risky to keep all of this information in one place. Hacking and identity theft have become multi-million-dollar industries. Thousands of people have their identity stolen every day. User data is commonly bought and sold as a commodity, and people rarely bat an eye when they find out that their data has been sold or stolen. And even worse, in a lot of cases, the particular party that's holding the data has a very high incentive to be dishonest about what that data is, or even to modify the data. So for example, my bank might have an incentive to not be totally honest about its balance sheets when it's talking to the government. Okay, so these are some problems with finance and larger systems that we want blockchains to solve, and we hope to do that. But the question is, what kind of data should we be putting on a blockchain? Because not everything is perfect for a blockchain. In general, we want to put anything that is permanent and that is not going to be changed. So any data that ought to be part of a record or a ledger can be stored here. Examples of this include financial records, personal identification information, contracts, medical and employment history, even votes for officials or public policy. These things that can be updated but don't ever need to be removed from the public record. Now, hopefully you are raising an eyebrow right now because I told you that a blockchain is a public ledger. So all of those applications that I just mentioned, or virtually all of them, require some kind of privacy. I certainly wouldn't want my medical history or my financial history or my votes to be publicly available to anybody who can see them. So how do we deal with the privacy issue? In fact, we have a more difficult privacy problem here. We don't just want to keep it completely private, that would be easier, but we want to sometimes reveal some parts of the data in very specific situations. This is what we call selective disclosure or selective reveal. For example, if I have a financial transaction, I might want it to be private and confidential, except in the case that the IRS needs to perform an audit and make sure that my balance sheets are solvent or whatever the IRS does. Or for, as another example, I might want my medical history to be private by default, but to become available to my personal doctor who has to be authenticated in some way. Or I might want to receive the results of an election and know which candidate won without having to reveal the exact vote count, since this might affect future elections. Knowing that a candidate didn't win by a lot this time might convince me not to vote for him next time, even though he's the candidate that I really want to win. Okay, so normally we achieve privacy like this and selective disclosure by trusting some specific party to keep the data confidential and to reveal the necessary data whenever the situation arises to any third party who might want to know. Now, as we mentioned, this is not only subject to hacking and abuse, but also requires that everybody trust whichever third party is coming in and doing this audit. It's not an option for me to, as a member of the public, to say, I would like to audit Chase Bank. I would like to make sure that my money is being moved around in the way that they say it's being moved around. That's just not an option. And so you might have heard of something called a private blockchain before and think that this solves our problem. But in actuality, a private blockchain is not private at all. It just means that you limit the set of users in the blockchain. But within those users, there's no guarantees of privacy. And the idea of a private blockchain doesn't address this at all. So we really need a new solution. So here's our central question that I hope we can answer today. How can privacy exist in a public decentralized system? All right, and now on to the main topic. So the answer to that question is one of the most popular buzz phrases in all of blockchain, zero-knowledge proofs. So just like in our blockchain discussion, we're going to talk mostly about what zero-knowledge proofs do and how we use them, as opposed to the details of their construction. And hopefully we can get to that in a future talk. All right, so what is a zero-knowledge proof, or a ZK proof, as it's often abbreviated? A zero-knowledge proof is a protocol between a prover and a verifier. And in this protocol, the prover wishes to convince the verifier that a particular statement known to both of them is true, without revealing anything else to the verifier. So the verifier should not learn anything except for the fact that the statement is true. And we call it a zero-knowledge proof because other than the fact that the statement is true, there's zero knowledge gained by the verifier during the protocol. As an example, our prover Peggy might wish to prove to Victor that her transaction X, which she doesn't want to reveal the details of, doesn't cause her to go into the red. And Victor might ask her to prove it. And usually these protocols take the form of some kind of challenge, followed by a response, and then repetition. So the idea is that if the prover can successfully meet all of these challenges with the appropriate response, then the verifier will be convinced that the statement is true, in this case that the transaction amount doesn't exceed the current balance, without learning anything else. Okay, so that is the standard kind of zero-knowledge proof. This is the most basic kind. But these standard proofs are somewhat inefficient because there's a lot of communication back and forth, and we have to repeat these challenges a lot of times. So one of the most popular and most widely talked about improvements on the zero-knowledge proof is called a non-interactive zero-knowledge proof, or a NIZK. So not only is the original interactive protocol inefficient, but it's also, if you think about it, not really a proof in the way that we usually think about them. So the classical idea of a proof is that I write down the proof, and then anybody who comes and reads the proof can verify that it's correct and can believe the statement for themselves. But in what I just described to you, Peggy sort of only convinces Victor that the statement is true. If another verifier were to come by and say, I also want to confirm that this transaction is valid, then they would have to redo the protocol with Peggy all over again, because they're not sure if Peggy and Victor colluded. If Peggy and Victor are actually on the same side and were colluding with each other to try to pretend that the statement was valid, Victor could just choose the perfect challenges to which Peggy always knew the proper response and produce a transcript that looks like she convinced him, but actually they were working on the same team. So future verifiers are going to need to repeat this protocol over and over again. Now, ideally, we would want a proof in the blockchain setting where multiple people can verify the transactions, no matter whether they're online or offline or in space. And so we really want something more in line with a classical proof. And that's what a non-interactive zero-knowledge proof offers. So some already interactive proofs can essentially be made into non-interactive zero-knowledge proofs using something called the Fiat-Shamir heuristic, which I'm not going to talk too much about here, but essentially replaces random coin flips with outputs from a collision-resistant hash function. Hopefully we can talk about that more in the future. It's a very interesting topic. But the end result, what you get out of this, is a single proof that the prover can post anywhere. And this proof is publicly verifiable by any verifier. So just to visualize this, instead of an interactive proof between Peggy and Victor, Peggy would perform the entire computation on her own and publish her proof of the statement to whatever place she wants to post it. And then any verifier who wishes to confirm that the statement is true can follow some specific protocol to verify the proof. And they don't have to talk to each other. All they need to do is access the single string that Peggy posted. Okay, so we've got a basic idea of what zero-knowledge proofs are and what non-interactive zero-knowledge proofs are. And the question is, how is this useful to our problem? So just to remember, we want our data on the blockchain to be confidential, but also auditable so that we can selectively reveal whatever data is necessary to any person who wants to audit us. And the solution is that not to store our data directly on the blockchain. Instead, we construct what's called a commitment, which you can think of as a hash function. So we take our data and we plug it into a hash function, and this produces a commitment that binds us to a particular piece of data, but also hides what that particular piece of data is. So the result is just a sort of random looking string that makes sure in the future that I can prove to somebody that my data that I committed to actually corresponds to that committed random looking string. And so the idea is to post my commitment to the data on the blockchain instead of the data itself, which doesn't reveal anything about the data itself, and then also post a zero-knowledge proof or a non-interactive zero-knowledge proof that confirms that the value I committed to is valid under whatever validity rules we've set in place. So back to our previous example, I would post a hash of my transaction, and I would also post a proof that says I know some transaction, which is valid, and when I plug it into my commitment protocol H, I get this exact commitment. And all of our verifiers can look at this proof, run the verification algorithm, and be convinced that I actually do know a transaction that produces this commitment and satisfies the validity rules. So this allows me to, instead of just convincing a single verifier, I can convince all verifiers that my data is valid without having to reveal my data in clear. So that covers how we work with blockchains and zero knowledge on a high level. Let's talk about some possible applications. So there are many possible applications of zero knowledge in blockchains, many of which involve verifying some kind of sensitive information, like your location or previous medical conditions or employment history, without having to reveal that information on the blockchain. And what zero knowledge does is it allows for lots of different kinds of verification, including verification of things like outsourced cloud computation or any of the things that I just mentioned. We've even had things like games programmed on blockchains where you can prove that you performed a move in the game that is legal according to the game rules, but not reveal your strategy to any of the other players. And this list might seem large, but actually we're just beginning to scratch the surface of all of the possible applications. Okay, so let's talk about some of the different sort of flavors of zero-knowledge proofs. Now, when I say flavors, what I mean is we're going to discuss what are some of the important qualities of a zero-knowledge proof system. And this will be crucial in order for us to be able to compare and contrast different systems and determine which one is the best fit for a particular application. So what makes a zero-knowledge proof system good or bad? How do we measure the quality of a zero-knowledge proof system? Well, the simplest metric would be to look at how much communication is required between the prover and the verifier. And so there's sort of two ways we can look at this. We can look at the overall communication in terms of the number of bits sent back and forth, or we can look at the number of rounds of communication. And both of these are very limiting factors in high latency networks. You find people focused on both, but overall, rounds of communication has seen a larger focus by the blockchain community, as evidenced by their emphasis on non-interactive proofs, which are one round of communication. We can also look at how efficient the verifier is. So how much time does it take the verifier to verify a proof, and how much space does it require in that verifier's memory in order to verify the proof? We can equivalently look at the prover's efficiency. This is an important metric to consider. Although in general, it's more important to consider the verifier because verifiers are often on more constrained machines. And one of the most crucial things that we're going to examine in further detail is we want to look at whether a zero-knowledge proof system requires some kind of trusted setup. And if you don't know what that means, don't worry, because we're going to dive into it much deeper. So what is a trusted setup? The basic idea is that a lot of protocols which solve some problem can be simpler if the players in the protocol begin with some kind of correlated random numbers. And so one example of this would be if two players wish to compute the sum. So here Alice holds the number A, Bob holds the number B, and they want to compute the sum of two numbers. Well, if Alice holds the number R, and then she can send A prime over to Bob, which is just the number A hidden by the value R. And then Bob, if he also knows this value R, can simply subtract that from A prime to get the sum. And then he can return that sum to Alice. So here, they're able to construct a really simple protocol for computing the sum based on the fact that both Alice and Bob know R. Now, there's some pretty big problems with using a trusted setup, the most glaring of which is that whoever initially creates these random values and distributes them to the players must discard them. If they do not do that, if they remember those random values, then they can use that randomness as a powerful weapon in order to prove false statements in the zero-knowledge proof system. And this is particularly bad in the financial realm, because if I am able to submit a transaction that's confidential, but which actually violates the rules of the game and creates new money when it's not supposed to, then this can result in inflation in the system that's not detected by any of the other players. So all of the other players' assets will become less valuable and they will not know it. So this is very, very bad. Now, there's one possible solution to this high risk, which is to, instead of choosing one person to create these random numbers, we instead get multiple parties to come together and produce the randomness together. And when we have them do this via a multi-party computation, we only require that one of the parties discards their randomness. And as long as one of the parties throws it away, then security is made. But We can alleviate some of this risk by having multiple parties produce this randomness together. So we can do this according to a multi-party computation protocol, but such a protocol is expensive and it's risky because, in fact, as if all of the players collude together and they keep their random values and they share them with one another, then the security of the protocol is still broken. So it incurs a high expense, but does not necessarily protect the protocol from this toxic randomness. And as an example from our previous slide, if Eve, the eavesdropper, knows the secret value R that Alice is using to mask her message, then she can actually determine the message immediately and know Alice's private input. So these are some of the problems with using a trusted setup in general, but why are these particularly bad for the blockchain setting? Well, first of all, players in the blockchain setting often have extremely high incentives not to discard this initial randomness, since it allows one to prove the validity of invalid data and thus behave arbitrarily without being detected. Now, if this task is distributed among multiple players, that process is expensive and it has to be repeated often. For example, whenever your blockchain undergoes a hard fork due to significant changes to the underlying system, you're often going to require a whole new multi-party computation to produce this trusted setup. And in the worst case, there's some systems like Hawk, for example, where every single time you produce a new smart contract, which is just a contract on the blockchain network, you have to produce an entirely new trusted setup. So this is very bad from an efficiency perspective and also from a security perspective. So what would the ideal zero-knowledge proof system look like with that in mind about trusted setups? Well, based on our initial conversation, our ideal zero-knowledge proof system, particularly in the blockchain setting, would be non-interactive, meaning there's only one round of communication and players don't have to talk back and forth. It would also have very short proofs as compared to the size of the statement you're trying to prove. It would have an efficient algorithm for both constructing these proofs and for verifying them. And it would involve no trusted setup. So now that we know how to evaluate a zero-knowledge proof system, let's take a look at one of the most recent zero-knowledge proof systems to be discovered, supersonic snarks, and see how it holds up to our analysis. Once again, we're not going to talk much about the construction of supersonic snarks, but we will discuss what they do and why they're effective. To begin, what is a snark? SNARK is an acronym that stands for Succinct, Non-Interactive Arguments of Knowledge. Succinct means that there are fewer bits in the proof than there are gates in the circuit that checks an input for validity. Or in other words, the proof is smaller than the statement that you're trying to prove. This is a particularly important property in the blockchain setting because using proofs like this significantly reduces the memory necessary to maintain the blockchain. A snark is also non-interactive, meaning it only uses one round of communication. And it is an argument of knowledge, meaning that the statement you're trying to prove is a statement of knowledge of some piece of data. In particular, knowing some input that produces the commitment that is placed on the blockchain. So you might have noticed that the succinctness and non-interactive properties are exactly two of the properties we wanted from our ideal zero-knowledge proof system. And in fact, an ideal zero-knowledge proof system is essentially a snark with no trusted setup and an efficient prover and verifier. So what are supersonic snarks? Well, supersonic is a brand new snark system designed by Findora, and in particular, it's the first snark to have each of these nice properties. So first, the proof is logarithmic in comparison to the size of the validity circuit or the size of the statement that you're trying to prove. as is the computation required by the verifier, also logarithmic in the size of the statement. The prover's computation is still practical. It's n log n in terms of the size of the circuit required for verification. And most importantly, the system is transparent, meaning it doesn't require a trusted setup. So what does all of this mean for blockchain? Well, supersonic snarks essentially mean that zero-knowledge proofs can now be transmitted, stored, and verified much more efficiently than ever before, and in particular without a risky and expensive trusted setup ceremony. It is the latest and greatest stepping stone on our never-ending path towards the perfect zero-knowledge proof system, and represents the best system that we currently know of. Now that we know a little bit more about the underlying technology, let's finish by discussing the impact that such technology can have on an industry such as finance, and discuss the details of Findora's vision of a decentralized Internet of Finance. To begin, what are the problems with our current centralized financial system? As they currently exist, financial institutions are opaque, they're inefficient, and they're high risk for both consumer and institution. Performing audits on paper documents managed and organized in institution-specific formats is difficult, expensive, and invasive. Maintaining such a system is costly for the institution and is slow overall. Clients' data stored in such a system is often mismanaged, abused, and hacked. And according to the Edelman Trust Barometer, only 56% of people globally trust the financial industry, which is worse than any other industry. So, what is Findora's vision? The Findora team sees the recent breakthroughs in blockchain technology as an opportunity to create one single global financial network, which balances both privacy and auditability. The resulting product will be a blockchain-based Internet of Finance, which will enable a large ecosystem of independent transactional ledgers to interoperate with one another. But what exactly is Findora? Technically speaking, Findora is a blockchain-based confidential transaction system outfitted with the latest and most efficient zero-knowledge proof technology. On a functional level, it works as a private and auditable ledger, where each transaction on Findora is encrypted, but at the same time, each transaction can be audited for compliance with respect to a particular policy. A Findora ledger on a single computer acts as a private and auditable database. But when run across a decentralized network, a Findora ledger can be used basically as a confidential Ethereum public network. And in particular, independent developers may write and deploy custom software to be deployed on top of the Findora ledger. Now, under the hood, there's a lot of exciting technology being applied within Findora, in addition to the efficient zero-knowledge proofs used for compliance. In fact, Findora uses a cutting-edge cryptographic accumulator model for storing the data, which means that client-side storage is actually constant and does not grow over time, as in traditional blockchains. Findora also makes a point of separating this storage model from the consensus protocol. This allows users to act solely as a validator without storing the blockchain in memory, or similarly, they could store and query the current blockchain without having to participate in the consensus protocol. We haven't talked about consensus here today, but hopefully we'll get to talk about it in the future. In terms of the level of privacy that Findora offers, it's one of the few services, along with Monero and Zcash, to provide private, unlinkable payments. Bitcoin and Ethereum are totally public, whereas classical centralized services such as Venmo are only visible to some trusted third party responsible for auditing. And as I mentioned, Decentralization naturally makes auditability more difficult since it can't be delegated to some trusted third party. You can see in this diagram that Findora and Ethereum are the only platforms supporting complex financial agreements which allow public auditing through decentralization. Other publicly auditable blockchain-based services support only simple single asset transfers and are not designed to prove compliance under complicated sets of financial rules. Findora, as compared to Ethereum, allows for these financial agreements to be private. Here are a few of the most popular privacy-preserving operations that Findora can support. Not only can you confidentially transfer your assets, but you can store confidential assets, confidentially send assets to a recipient from multiple sources, as well as perform privacy-preserving computations like sealed bid auctions, fair lotteries, dark pools, and more. On the auditability side, Findora allows users to prove a wide range of compliance properties about said confidential assets. For example, you can prove the solvency of a balance sheet, prove that an account balance or transfer amount is within a certain range, prove that a particular issuer or type of asset is authorized according to some whitelist, distribute capability-specific keys for viewing specific necessary information, allow an asset issuer to confidentially trace the transfer path of their asset, or even prove that a particular transaction is compliant with the terms of contract. Findora's balance of privacy and auditability makes it the ideal infrastructure for a private decentralized finance. We're very excited to see what Findora is truly capable of, and that's why we're calling on the developers in the community to start imagining what they can create on top of a decentralized financial platform. It's the members of the community who will use the JavaScript API provided by Findora to design the Internet of Finance. If that sounds interesting to you, please submit your contact information and we will contact you about possibly joining our testnet. Testnet users will gain access to the first version of the Findora network and the JavaScript API and are encouraged to build and deploy financial services on top of the Findora blockchain. You do not need to have any particular experience with blockchain, zero knowledge, or finance, just the desire to build new and exciting technologies for the decentralized financial world. Thank you all so much for your attention and for inviting me here today. This concludes the presentation, and now I would be happy to take any and all questions. Thank you.